Welcome back, everyone. In the last video, we talked about how we can compute certain integrals geometrically if the area is a familiar shape. And in this video, we're going to introduce a more robust way of evaluating integrals that does not require the use of geometry. So even if the function creates an area that is an unfamiliar shape, we can still potentially evaluate that integral. And this technique is called the fundamental theorem of calculus. And to build up to this big theorem, I want to remind us of the distance and displacement problems that started this whole topic. So let's say we have one function, little f of t, and that function is the velocity of an object over time. Let's let big F of t be the position of the object over time. I know it's a little weird to use little f and big F, but that's what everybody uses in this context. And recall that the displacement, that being the change in position, is equal to the signed area under the graph of the velocity function. We took all of the area above the x-axis and subtracted away the area below the x-axis. And I want to focus on displacement, not distance, because computing displacement is more in line with what a definite integral computes. The definite integral of the velocity function computes the change in position from one time to another time. But if I knew the position function, then I wouldn't have any need for this definite integral. Because another way I could compute the change of position, if I know the position function, is to take the position at the end and subtract away the position at the beginning. That would be big F of b minus big F of a, because capital F of t represented the position of this object over time. So what I'm getting at here is that if I'm computing the definite integral from a to b of the velocity function, that's equal to the position function evaluated at b, subtracted away the position function evaluated at a. And so if I knew what the position function was, this would be a very easy computation. I would just plug in b, and then plug in a, and then subtract the two. The big issue there is that I'm not always going to know what the position function is. But if you recall, there's an idea that connects the velocity function and the position function, that being the derivative of the position function is velocity. So if I'm taking the definite integral of a velocity function, I just have to figure out, is there a function out there that when I take its derivative, I would get this velocity function? And whatever that function is, that would be the position function. And if I could find that position function, I'd be able to evaluate this definite integral fairly easily. And these ideas here are exactly what make up the fundamental theorem of calculus. And what the fundamental theorem of calculus says is that if I have a continuous function, little f, on some interval from a to b, and there's some function out there, capital F, that when I take its derivative I get little f, then the definite integral from a to b of f of t dt is equal to big F of b minus big F of a. And these are exactly the ideas from the previous slide, just a bit more concise. And so the big question when you're integrating a function is going to be, what's the function out there that when I take its derivative, I get the function that I'm integrating? And that function is known as the antiderivative of little f. And finding that antiderivative is oftentimes going to be easier said than done, and you're going to spend a big chunk of time in Calculus 2 just talking about ways that you can find the antiderivative of different kinds of functions. Much like once we learned what a derivative was, we had to spend a couple of weeks learning the chain rule, the product rule, the quotient rule, and so on. But for now, don't worry about those techniques yet and just focus on the big idea here. And I do want to highlight that this function, little f, does need to be continuous on the interval that you're integrating over. And it is possible to find the definite integral of some discontinuous functions, but those are different techniques that you'll learn later on. To use the fundamental theorem of calculus, your function, little f, does need to be continuous. And this is because the way that you rigorously prove the fundamental theorem of calculus, which we won't do, requires the idea of a Riemann sum from earlier, and that idea of adding up the area of those rectangles doesn't really make sense if the function f is not continuous. And so to use this technique, the fundamental theorem of calculus, your function little f does need to be continuous. Just recapping this one more time, if I am integrating a function from a to b, I got to figure out what its antiderivative is, and then I plug in b, and subtract plugging in a to that antiderivative. So let's do an example, and let's evaluate the definite integral from 0 to 2 of 2x dx. And this is an integral that we could actually evaluate geometrically using the techniques from the previous video, but I picked this so it'll allow us to verify that these two techniques coincide with each other. And the function 2x is continuous, so I can definitely use the fundamental theorem of calculus. And to use the fundamental theorem of calculus, I have to find a function such that its derivative is equal to 2x. That would be the antiderivative of 2x. And is there such a function? And the answer is yes. That function is x squared. If I take the derivative of x squared, I get 2x, and so x squared is an antiderivative of 2x. And so the definite integral from 0 to 2 of 2x dx is equal to this antiderivative evaluated at 2, subtracting away the antiderivative evaluated at 0. And I'm using 2 and 0 because those were the bounds of the definite integral. Now, what is the antiderivative evaluated at 2? Well, the antiderivative was x squared, and so if I evaluate that at 2, that's going to be 2 squared. And then evaluating it at 0 will be 0 squared. And if I simplify that, I get 4. And the reason that I'm squaring these numbers is because the antiderivative is x squared, and so if you have a different antiderivative, you should not be squaring it. You should be doing whatever that function is defined to do. And so this is it. This is the answer to the definite integral from 0 to 2 of 2x dx. It's equal to 4. And we were able to find this without doing any geometry or having to graph anything. And to recap the process, we first ask ourselves, is there a function out there that when I take its derivative, I get 2x? The answer to that was yes. That function is x squared. If I take the derivative of x squared, I get 2x. And so x squared is an antiderivative of 2x. And then I plug in the bounds. I plug in 2, I plug in 0, I subtract them, and I get 2 squared minus 0 squared because the antiderivative was x squared. And I simplify that to get 4. And just a little bit on notation, this second step here, where I took the antiderivative evaluated at 2, subtracted away the antiderivative evaluated at 0, we don't usually write that step like that. We would write the antiderivative, which in this case was x squared, and then we write this bar, or sometimes a bracket, and at the top of that bar I would write the upper bound from the definite integral, which was 2, and at the bottom I would write the lower bound from the definite integral, which in this case was 0. And this signifies that you've found the antiderivative, which is x squared, and in the next step you're going to plug in 2, and then subtract plugging in 0. Now, one thing you might have noticed in this problem is that I used the phrasing an antiderivative. I didn't say the antiderivative, because there will often be, well, there always will be more than one antiderivative. Say for my antiderivative, instead of x squared, I'd chosen x squared plus 1. If I take the derivative of x squared plus 1, I get 2x, and so x squared plus 1 is an antiderivative of 2x. And that's because when I take the derivative of any constant, it's going to be 0, and so for my antiderivatives, I can add any constant I want to at the end, and that will also be a valid antiderivative. Now personally, when doing these definite integrals, I would leave off that constant because it doesn't do anything, it just clutters up the problem, but if you did include it, it would not be incorrect. And just to demonstrate that I can get the same answer, let's evaluate that definite integral, but use this new antiderivative instead. So if I want to evaluate the definite integral from 0 to 2 of 2x dx, an antiderivative of 2x is x squared plus 1. And notice I'm using the more commonly used notation here, where I write the antiderivative, and I have that bar at the end where I include the bounds that I'm going to evaluate this antiderivative at in the next step. And from here we plug in 2, and then subtract plugging in 0. And even though the antiderivative is different, notice how I have a plus 1, and then I'll have a minus 1. And so whatever constant I include in this last step will simplify itself away. And going back to the graphical perspective, don't forget that this definite integral represents the area under the graph of y equals 2x on the interval from 0 to 2. And since we got an answer of 4, the area of this shape here should be 4. And this is a very familiar shape. It's a triangle, and you could confirm that if you found the area of this triangle, you would also get an answer of 4. And so this verifies that this new technique, the fundamental theorem of calculus, gives you the same answer as the geometric technique. But the fundamental theorem of calculus is a little bit better, a little bit more general, because you'll be able to use it in many situations, even where the area is not a familiar shape. And to close out this video, I want to add that this fundamental theorem of calculus is called the fundamental theorem of calculus because it ties together two huge ideas in calculus. The idea of the derivative and the idea of the integral, which at first glance seem very different, The derivative is the slope of the tangent line, and the definite integral is the area under the curve. And this theorem here links those two ideas together.